Yeah, hi all. Like, are you guys attending the sessions which are conducted on Friday and Saturday? Like, any one of you can just tell me?
Yes, sir.
Yeah. So, the questions are not repeating, right? Which I am taking and others are taking?
No, sir.
Okay, okay, fine. And roughly, can you tell me how much attendance is there in that sessions, other sessions?
There are also 9 to 10, 9
Okay,
to 10 students.
near about 10. Okay, okay, sure. Thanks. Yeah, we will start in like 1 minute or so. Okay, then let's start this session, which is third session taken by me. So I welcome you all to this third session, which will be hosted by me, Swanand Telpande. As you may know my name. Otherwise, some of you who don't know my name, I am Swanand Telpande, a PMRF student. I am currently pursuing PhD in ISC Bangalore. So I need to take these sessions for you guys to understand like how to solve the gate previous year questions, which will help you like solving like in better understanding of time management and how much time you should devote in particular question, and you will get a feel of like what kind of questions are asked in such gate examination. So today I have taken like four questions which are basically knowledge based. So we don't have to solve any like have a formula and solve any question, or it is basically four options are given and you need to pick one. So two are from like manufacturing processes and one is from like mechanical metallurgy. Sorry, two are from mechanical metallurgy, one is from manufacturing processes, and another we will let's see. So again we will do the same thing. I will project the question for like let's say 2-3 minutes and you try to solve the question, and later we will go through the complete solution of that question. So I will start by presenting my screen. I hope you can see my screen now. Can you see my screen?
Yeah, sir, it's visible.
Yeah, it's visible. No, okay. So I will project first question. I will give you like 2 minutes time only. It is more than 2 minutes are not usually required for this question. So you just try to answer this question. Then we will go through the solution. One more minute and then we will solve this question. Okay, so one of you have guessed A. You require more time or shall we proceed with the answer? This is dislocation theory based, like how slip occurs and everything. What are the different types of slip, and these are the concepts here and there here. So if you have gone through dislocation theory in mechanical metallurgy, you will be able to answer this question. So let's start. I will go through the solution. This is question number 18 from GATE Metallurgical Engineering paper 2016. A plastically deformed metal crystal at low temperature exhibits wavy slip line pattern due to, there are four options. First is dislocation pileup. Second is large number of slip systems. Third is low stacking fault energy. And fourth is dislocation climb. So in order to answer this question, first we need to understand what is wavy slip line pattern. So basically a wavy slip line bottom is formed because of multiple slip on different planes. So let's say we have 2-3 different planes and on that multiple slip is occurring, and more often it is observed in open structures. Like open structure, I mean to say in BCC, where we don't have any closed packed plane as such. Like in FCC 11 is the 111 is the closed packed plane. In BCC, although like 110 we consider is as a closed packed plane in BCC, it is not actually that if you calculate the planar density of that plane. Hence wavy slip pattern occurs in those systems. And also as it is mentioned at lower temperatures, what is there is like less number of slip systems are activated, because this movement of dislocations require higher temperature. So large number of if you have read about Schmidt factor, like the mostly aligned, like at 45 degrees, if the plane is aligned to the principal normal direction, then slip will be activated in that slip system. Otherwise other slip systems won't be activated. Hence at lower temperature the tau CRS is required to activate sleep is higher. Hence, less number of sleep systems are activated at lower temperature. And low stacking fault energy means greater width of the stacking fault. If greater width of the stacking fault is there, then cross slip of screw dislocations will be difficult. Hence, it will give rise to only planar slip. So multiple planes won't activate slip. And as you know that dislocation crime is also like activated at higher temperature, which is not active. Like one dislocation, if you consider this, if you consider this as a plane and this is one dislocation and this is another plane, this is another dislocation. So if this dislocation wants to go above the plane or below the plane beneath that, it requires certain temperature and moment of vacancies, and vacancies are like thermally activated process. Diffusion of vacancies is thermally activated process. Hence dislocation climb is also not the reason for that. Now again coming to the question, like as a plastically deformed metal at low temperature, so low temperature dislocation climb is not active. Low stacking fault cannot lead to multiple slip on different planes because the width of the stacking fault is higher, hence no cross slip occurs, and a large number of slip systems are not activated at lower temperature. So what it does is like the dislocations which are moving like on different planes, they try to come at same point and form jogs, or like if this location is moving on this plane and this like on this plane one dislocation moving, these are trying to come at the same junction. So here these dislocations will pile up, and this pile up will lead to like slip on some different plane. Hence this will give to dislocation pile up and later wavy slip. So the answer is A. So I hope you have understand. You can ask me doubts regarding all these things. Yeah, you have any questions or doubts regarding this question, like what is wavy slip? Wavy slip is caused because of like multiple planes are like active, and like more and more dislocations are coming to a junction where dislocation pileups takes place. Hence we get a wavy structure out of that. Any questions, doubts regarding this question? Okay, then we will like start with next question. I will project next question. This is the next question. Try to answer in 2 minutes, then we will go to solution. One more minute and then we will start. One question is there regarding to the previous question. Slip not happen at room temperature means how the deformation is occurring. Okay, it's not like slip is not occurring at room temperature. Slip occurs at room temperature, but the number of independent slip systems, like I will show you in like how the tau CRSS changes, like on this slide I will show you. So let's consider a graph where this is a function of temperature and this is tau CRSS. So what happens is like it will be like this, usually the curve. So as you go towards very low temperature, I am not talking about room temperature, I am talking about very low temperature, like like just above the Kelvin, like minus 100 Kelvin or so. So what happens at sub-zero or cryogenic temperatures is that the tau CRSS required to like cause the deformation by slip. There are basically two types of deformation. One is by twinning and second one is by slip. So what happens is like because this tau CRSS is very high, this is the stress required for twinning, which is ideally flat. At any temperature the stress won't change. So this is tau for twinning. Okay, so this is constant. So at a particular temperature what happens is like tau CRSS is higher for slip than twinning. So the material tries to deform by a twinning manner, and as you go on increasing the temperature, this tau CRSS falls below twinning. Hence now more and more independent slip systems get activated in the material, which means like which homogeneously deform the material. So as you can see here, so the room temperature will be here, somewhere here, T room temperature. So in some materials this crossover happens above the room temperature, and in some materials this crossover happens below the room temperature. In case of FCC this is the case, whereas in HCP you may find, like let's say in magnesium, you will find more twins in microstructure. Because of this case, as at room temperature also there are not many independent slip systems active at room temperature, hence the another mode of deformation is also taking place, which is basically twinning. Hence at room temperature slip occurs, but I am saying about at low temperatures, cryogenic temperatures, not at room temperature. I hope this is clear. Okay, any other question regarding to previous question? Otherwise we will go to the solution of next question. Okay, so we will go to the solution of next question, which is on creep. So okay, so I think you may have, if you are in final year or so, you may be knowing regarding creep, what is creep and everything. Let's again start with this. This is question number 19, GATE 2016 Metallurgical Engineering. creep resistance decreases due to A. Small grain size, B. Fine dispersoid size, C. Low stacking fault energy, D. High melting point. So firstly, what is creep? So creep is defined as time dependent deformation at elevated temperature and constant stress. So if we let's say if we have a material, we are keeping it at a temperature T and we are applying uniform stress, let's say compressive here. So let's say P is the load applied, which is giving generating compressive stress throughout this cylinder, and we are holding it at time T. So what will happen if you are below the yield stress also, this material after like a long time will try to deform or like relieve the stresses caused by this load. Hence, this deformation caused by a constant stress at a higher temperature is basically creep. And creeps are of two different types. One is diffusion creep and another one is dislocation creep. So what happens in diffusion creep is like diffusion of atoms takes place from one region to another. So there are three modes from where diffusion of atoms can take place. First is through bulk, second one is through grain boundaries, and third one is the surface diffusion, which we are neglecting here. So two are the major diffusion mechanisms from where the atoms or vacancy can migrate from one place to another. And second one is the dislocation creep, which occurs by moment of dislocation through lattice and causing strain in structure. So these are the two different types of creep mechanisms, and creep usually occurs above 0.7 of melting point. This is given because as we are talking here of diffusion of atoms and vacancies, so diffusion is a like temperature accelerated process. At higher temperature diffusion will be faster, hence for vacancies and atoms higher temperature is required. So if we consider higher melting point, in higher melting point what will happen is like we will require higher temperature to cause the same creep in a material. Hence the creep's resistance will increase if we have high melting point. And let's talk about low stacking fault energy. Let's say what happens in dislocation creep is like one dislocation is moving in certain plane, and has some hindrance here, so it cannot move here. So what it does is like it can cross slip this dislocation to some another plane and try to slide here. So using cross slip, what happens is like dislocations try to move away from any hindrance and give plastic deformation by its movement. So what happens when low stacking fault energy is there, it gives like a more stacking fault width is there. Hence if more stacking fault width is there, it is difficult to cross slip for a dislocation. Hence decreased mobility of dislocation. If decreased mobility of dislocation is there, creep resistance will increase, not decrease, because creep resistance is because we should hinder the path of dislocations. Hence C is also not the option. Now coming to fine dispersoid size. So let's say we have one dispersoid here, and this complete is a matrix and one dislocation is trying to move here. So let's say it is going like this on this slip pen, which it encountered by a dispersoid. So what it will have some hindrance in the moment. So what it will do is like it will try to like shear this, like shearing will occur like this. If you have studied this, shear will occur like this, or it will try to just go around this dispersoid. So what is happening because of this fine dispersoid is it is creating more hindrance to the dislocation moment, which is basically increasing the creep resistance. Hence fine dispersoid size is also not an correct option. And smaller grain size, let's consider that I have a structure like this where these are different grains. Okay, and one is with bigger grains. Now coming to the same point, as diffusion creep occurs by diffusion of atoms and vacancies through bulk oblique grain boundaries. So here you can see the grain boundary fraction is higher. Hence the diffusion at a particular temperature, if both conditions are same, like for this also temperature and stress are constant. So what will happen is like atoms and vacancies can migrate easily through this large number of grain boundaries than this, because here the grain boundary fraction is less. Hence what will happen is like this material will creep faster than this material because of diffusion is high here rather than here. Hence this will decrease the creep resistance, and which is A, because of smaller grain size and a large number of the grain boundaries fraction. Hence the correct answer is A here. I hope you understood this question. This is fine. You have any doubts on this question? What about D option? Okay. Yeah, that's what I was saying. Like D option is high melting point. Let's say I have two materials. Just a second. Are you able to see my screen? Hello? Hello?
Yes, sir.
Can you see my screen? Yeah, I guess now you can see my screen. Some problem is there. Okay, I will just try to answer verbally. Like let's say if I have a 1000 degrees Celsius temperature, or let's say okay, 1000 degrees Celsius temperature. Now I take two different materials where the melting point of one is, let's say 1400 degrees Celsius, and another one is 2000 degrees Celsius. So there are two things. One is like creep is basically accelerated process at higher temperature. So if you consider 0.5 tm, 0.5 of tm of one material will be 700, and for another one will be 1000, like that. So if we consider these two materials, so according to you, in which material creep will be more faster? Like where the like 0.5 tm will be 700, or where 0.5 tm will be 1000? Obviously where 0.5 tm will be lower, like let's say 700, because we are keeping both materials at 1000. Hence higher the melting point, the creep resistance you are increasing of that material will be increasing at a particular temperature. I hope this is clear. Is this clear, Chintu? what is the fine dispersoid soil? Okay, so basically a material contains like precipitates or dispersoids. So these are basically added in a material to increase the creep resistance. So creep usually occurs because of diffusion and dislocation movement. So if we have something in my materials so that the dislocations are not able to move, or they are causing like higher resistance for their path, hence then what will happen is like the dislocations would like try to overcome that obstacle, hence in that more energy will be required. And if more energy will be required, then the creep resistance will increase to get the same amount of creep strain in my material. So fine dispersoids are basically put so that we don't have any like we have enough obstacle for the dislocation moment. I hope that is clear, Devendra.
Yes, sir.
Cool. So if there are no questions regarding creep, then we can start with third question. Okay, so let's move on to third question. Again 2 minutes time I will give, and we will solve the question after 2 minutes. Okay, this is regarding the manufacturing processes, metal joining processes. Now you have to classify the welding processes according to their heat affected zone. Let's say we have these two materials which we need to join using three different processes. So we have to determine how much will be the heat affected zone. So it will be somewhere away from the joint. So we have to know which will be farther from this joint, in which of the process. We have to arrange in that way. This will be H A Z. So I am here mentioning the reading material also, which you can follow. This will be available on nptel.ac.in website, where you can access all these videos and go through it if you don't know this concept behind all these processes and everything. Okay, so I can see two answers, C, B. Okay, shall we start with solution then? C, B, D. Okay. So which one of the process you think it will be least, like the heat affected zone will be as less as possible? Which can be among these three techniques, which will be the robust process that you have a joint also with very less heat affected zone? We are talking about three techniques: laser welding, submerged arc welding, and metal arc inert metal gas welding. These are common processes of welding used in industry. Some has other advantages over one another. Laser beam welding will be have least heat effect. Okay, good. Okay, let's start with solution then. Yeah, so Manikan is saying that high energy beam will be laser. Yeah, we have to look at two things also here. First thing is like, what is the high energy beam, as you have rightly pointed out, how much localized that beam will be, and how you are extracting heat also. Three different things are there which will determine the heat affected zone in every process. So let's start with this. This is question number 21, GATE 2016 Metallurgical Engineering. Of the following welding processes, P is laser beam welding, Q is submerged arc welding, R is metal inert gas welding. The width of heat affected zone in decreasing order. So the options are like P greater than Q greater than R. B option is Q greater than R greater than P. C option is R greater than P greater than Q. And D option is P greater than R greater than Q. So first we will talk about laser beam welding. In laser beam welding, the laser conducts a series of short pulses that hit the material in exact places that we have to join. Basically, it is too localized to cause any heat affected zone. All the energy of the beam will be falling on the place where it needs to be joined, and the heat will be extracted faster as it is very localized, so it results in very small heat affected zone. So we should expect among all these processes that the least heat affected zone will be in case of laser beam welding. Second one is the submerged arc welding. The flux, here in submerged arc welding we use flux to isolate the molten material, which prevents splatter and contamination of the joint. Here the energy is confined inside the flux, leading to a large heat affected zone. And this flux is basically of oxides, chlorides and everything, which are basically the refractory material. So if you consider the amount of energy you are putting into the joint, and the heat extraction rate because of this refractory material will decrease. If the heat extraction rate decreases, it will try to conduct that heat through the two welding pieces. Hence larger heat affected zone will be occurred in submerged arc welding than the laser beam welding. And third one is metal inert gas welding. Here rather than flux we use inert gas to shield the molten material such as argon or helium. Hence it is by default submerged arc welding will have the most heat affected zone, because the heat transfer is not taking place because of the flux which is shielding the molten material. Hence the heat will be stored in the material only, which will create a large heat affected zone. And in laser beam welding it is very localized, hence the heat affected zone is very small, and metal inert gas welding lies in between that. So the correct answer is answer B, where Q is most, then R, then P, where laser beam welding has the least heat affected zone. I hope I am clear with the solution. You can ask me doubts regarding that. Is this fine, everyone? Any question?
Yes, sir, fine.
Yeah, okay. How can I say the HZ with current density? Current density. Okay. When you do arc, there is like some energy you are putting in. So if you increase the current density, then more region will be melted. But it will be it will depend on the same thing, like how the heat is extracted. Let's say if we have higher current density, then the electrode will melt faster. But the heat affected zone, which I think would be same only, it should not increase. It won't depend on current density according to my knowledge, but I need to cross check this. It depends on how much like that in two joints, how much space you are like heating up. In first case, like if the electrode thickness is higher and you are melting that complete electrode in one go, then the like the energy which you are providing is very high and heat extraction rate will be slower. Hence in that case the heat affected zone will be larger. But here increasing current density will speed up the process rather than like increasing the heat affected zone, which I think. But you need to cross check this once in a like a reference material. Okay, so coming to the last question, like we are like okay with time also. Okay, last question we will take, which is just a second, which is again 2 minutes to answer this question, again from manufacturing processes. Railway tracks. What is the manufacturing process of railway tracks? Like I will give you 1 minute only to answer this. If you know, you can answer, otherwise you need it's like you cannot take time to answer this. If you know, you can answer it straight away. Four different manufacturing processes are given: forging, extrusion, dip drawing, rolling. So you have to find out from which process railway tracks can be easily manufactured, and it should be commercially viable also. Like many techniques can be used to do that, but one is the commercially like industrial practice technique, which is generally used to like manufacture railway tracks. I hope some of you may have answered this question. B, 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 B. Okay. Let's start with this. This is question number 22, GATE 2016, Metallurgical Engineering. Railway tracks are typically manufactured using what process? A is forging, B is extrusion, C is drip drawing, and D is rolling. So this is a schematic which tells you that how from steel making, how the railway tracks are manufactured. Basically, this is in extractive metallurgy. You may have known that steel making, that from a basic oxygen furnace, how and to ladder furnace, secondary steel making, how you get steel, and after that you cast that steel using a continuous casting process, and after then rolling is done of these blooms billets. So rollers are like designed in such a manner that you will get the exact shape of the railway track. Here you can see the schematic of rollers, how these rollers are designed, and bloom passes through these rollers to get this shape. Hence the correct answer is rolling, which is a manufacturing technique mostly used to like manufacture railway tracks. And many of you have suggested that extrusion is also there. Even forging can manufacture railway tracks, but this is the commercially viable process, rolling, where you will have a designated roles like this as shown in the schematic, where directly if you can pass the broom through these rolls, manufactured finished product railway track will be there. Hence the correct option is option D, rolling. I hope you could understand this. Like yes, extrusion also like can be used, but like commercially rolling is preferred over all the processes, because like if you have a bloom, you can directly pass through the rollers and you can just get a complete railway track out of it. In extrusion you have to like have a die of that thing, and then you have to pass with lot of pressure, so it will be more energy consuming process rather than rolling. I hope this is clear, because many of you guessed B, extrusion, as the answer. Okay, if you don't have any doubts, let's stop this session for today. And in next session, I guess we will mostly start with 2015 questions, some numericals and some knowledge-based questions. So other questions of 2016 gate paper will be solved by other persons. So we will complete 2016 paper by this week completely. Then we will move forward to 2015, and we will go like by that previous years like 2014-13, like that we will proceed then. I hope this is clear, and you can suggest me like what you want extra in these tutorials, so that you will be benefited more out of these sessions. Okay, if you don't have any doubts, let's meet next Wednesday with some other questions. Thank you everyone. We need test, sir. You want to appear for test? Test, I don't think so. Like we will be able to organize any test. But the thing is like there are many test series. I don't know about like whether NPTEL organizes any test series or not. So if you can, like one thing you can do, like we are solving previous year questions like that. You can solve previous year questions of many papers and just keep 2-3 papers without any, like you cannot see any question of those 2-3 papers, and when you think that you are ready to give a complete gate paper, just try to solve that previous year paper. Let's say 2011, you have not seen any question of that 2011 paper. So what you try to do, revise all the concepts beforehand and then try to appear for that 2011 gate paper in 3 hours and check yourself where you stand in that paper. That will help you to know which subjects you are strong with and which subjects or concepts you need to revise more. Like I don't think I will be able to perform like conduct any test here, just that you can guess the answer before I start with the solution. That's all I think I can do here. I hope it is okay. Okay, sure. In next class we will meet next Wednesday 6 to 7 p.m. We will have some 4 more questions. Thank you.